So thank you very much. And before I continue my discussion, let me show you this table. This I took from my recent review article. This is a comparison between Elliptic prediction here and the lattice confirmation. And actually, it is not with, oh, by the way, this must be yours. So, it is not really known, but already the SU4 simulation falsifies the prediction by Svetitsky and Yaffe. So they conjectured that the SU4, 5, or whatever, these are the n symmetry should be enhanced to U1, and U1 is the n with a uniformly large n. Okay, and so then if it is the case, then the NTU second order phase transition belongs to O2's universality class, and with that consideration, they identified some critical exponent, but it turns out that the realistic situation should be a first order phase transition. So actually, so this simulation already falsifies so their conjecture. And also the SU4, very interesting simulation of the case of SU4 in 2 dimensions that was done by Philip and Oliver Young, yes, with so very funny prediction with varying exponents. Anyway, so this is very exotic.
Presumably it's first order, actually.
Huh?
The latest simulations indicate by Uwe Wieser and company indicate first order.
First order for this? Oh, really? Okay. This table must be corrected. Anyway, and so let me show you one more figure that is the last part of this review article. This is a bit lengthy, but at the end of this review article, yes, I actually discussed 2 possible phase diagrams. So this is a complicated phase diagram as described by Philip. But here you see, so I removed many of the complicated structures, and so okay, this is also one possible phase diagram, and this is becoming more and more likely candidate nowadays. Okay, but it is always easier to add something on top of something, right? But you know, erasing anything from the established picture is always more difficult, or it's a more heroic attitude. Okay, and so already I was attacked by several people, and so I had a very bad fight with some people. Okay, coming from this the proposed phase diagram. Anyway. Okay, so we will see which is the answer. So this is just a comment about the inspired by Philip's lecture. And so about my lecture, actually I forgot to mention about the importance of the vector interaction for the QCD critical point. So as I explained, this metastable state in terms of the one particle energy is the sufficient condition to have the first order phase transition, and so you can get a critical point if this is the case at 0 temperature. Okay? But if you have a vector type interaction like this, okay, then this produces the energy proportional to a density squared. And that means you have to add a linear rising term on top of this potential shape, okay, this energy shape. And then this minimum is pushed up by this contribution, and that means this minimum is gone if this interaction strength is large enough. And indeed, this is the case if this coupling strength is comparable to the scalar channel, I mean the chiral condensate channel, and that is quite a reasonable value. Okay, you cannot exclude the existence of this type of interaction from the symmetry consideration because this is completely chiral symmetric. Okay, so the higher order interactions can easily generate this type of interactions. Okay, and so so this is one of the reasons why the QCD critical point can be washed away by higher order interaction effects. Okay. So this I forgot to mention. Okay, so let's go. Yes, so and I explained Kokyo ni blah blah blah, and then yes. Okay, so if the first principle calculation is possible on the lattice, that would be fantastic. However, that is impossible due to the notorious sign problem. And then what is a sign problem? So let me explain the sign problem using a very simple model description. Okay. So let's keep A4 background only. Okay. Then this is good enough to see the sign problem. And then you can analytically compute the Dirac determinant. Okay. And after the integration along the temporal direction, this is what you get. Okay. This is just the same as the ground partition function for free particles. But the only difference is the existence of this background. And A4 is something like imaginary color chemical potential. So you have exponential A4 here that can be translated into L and L dagger, Fourier group and anti-Fourier group. Okay? And then, so it is obvious that you can have complex phase from this. Why? Because if this is zero density, then okay, if there is no mu here and here, okay, this weight and this weight, they are the same, and so this is the sum complex number times the complex conjugate. Okay, so this should be the real number, but here the weight is different. Here exponential beta mu, and here you have exponential minus beta mu, and so naturally this complex number is not compensated by the complex conjugate. Okay, this is no longer complex conjugate if you have finite mu. So the determinant, the whole quantity, is a complex number. Okay, and that you can see from the explicit calculation. Okay, so you can take some special gauge in which the Fourier group is diagonalized in this way, and then, as I explained in the context of the bias potential, this momentum integration, this determinant should involve the momentum determinant. Okay, so if you take the trace, then if you take logarithm, then this is trace log. Okay, and that trace involves the momentum integration, and that momentum integration is possible. Okay, that you can perform analytically to find this expression. Okay, this simple expression, and so this is nothing but the bias potential with very small modification. The difference is this factor 2 and this 1, and this 1 coming from the difference in the boundary condition. Okay, so instead of periodic instead of a periodic boundary condition for gluons, now you have to impose anti-periodic boundary condition for fermions, and so you have to add 1. Okay, if you add 1 here, then that means this pi. Okay, I pi times 5. So here you have extra factor exponential I pi. That is minus 1, right? And then in this way, so you can take account of the difference in the statistics, and also this too. This comes from the difference between the fundamental representation and the adjoint representation. Okay, and also you have some chemical potential term. Okay, and obviously this phase. Okay, this phase factor here. Okay, this is complex. Okay, and indeed you can plot this the imaginary phase factor as a function of a gauge field background phi 1 and phi 2, and of course the phi 3 is determined by the condition that this product should be 1. Okay, determinant L is 1, so phi 3 should be given by minus phi 1 minus phi 2. Okay. Anyway, so you have a very non-trivial structure. The imaginary gamma is a very non-trivial function of the gauge field background. So this is how you can see the sign problem perturbatively. Okay, and yeah, it is very interesting that the sign problem is not really a particular very special problem on the lattice, but you can see the sign problem even in the perturbative calculation, right? One loop calculation is sufficient to see the sign problem, okay? Anyway, so because this determinant is complex, so it is no longer possible to interpret this as the sum of weight of probability, okay? Then the Monte Carlo simulation is impossible. That is a sign problem, okay? And so you may think that maybe still it is useful to do some simulation without the phase factor, okay? Just take the absolute value of the Dirac determinant, and then, anyway, let's do simulation. You may think so, but this is not a good idea because this determinant, the absolute value squared, means that you have to multiply some complex conjugate partner here, okay? And here you have complex conjugate. That means instead of L, you have to have L dagger, and instead of L dagger, you have to have L, okay? And that is actually equivalent to the replacement of mu with minus mu, okay? And that means this system, this phase quenched system, is equivalent with isospin system, okay? Isospin finite, the system with finite isospin chemical potential, okay? So that means if this mu becomes greater than the half of the pion mass, you must have pion condensation, okay? Even before you go to the nuclear matter or finite density system, you have some system that is very different from the system you want to have, okay? So there is no hope to get any useful information about the finite density system by doing a phase quenched simulation, okay? And interestingly, from this form, you can see the equivalence between the baryon chemical potential and the isospin chemical potential in the radiancy limit, okay? This is first pointed out by Tom Cohen in 2004 from more general consideration or diagrammatic techniques. But from this simple model form, it is very easy to confirm this equivalence because, okay, so let's consider the expansion of this determinant in terms of the Fourier group L and L dagger, okay? And then you have to do the group integration when you take the expectation value, okay? And then the leading order is trace L, okay? If you expand this determinant 1 plus something, then the leading order is trivially 1 plus trace something, okay? But the next order is a bit complicated expression, but of course it involves more than the 2 or 3 or 4, or anyway, more L, okay? More and more L's. And then you have to do the group integration with respect to this Fourier group matrix. And then every time you pick up the color singlet component from this matrix structure, you have a 1 over NC suppression, okay? So obviously, this trace L is a leading order contribution, and then there is no difference at all between isospin chemical potential and baryon chemical potential, right? Because, okay, this is just addition, not multiplication, okay? This is just addition. So, you know, the different flavors do not talk to each other, but they give completely separate contribution to the partition function, okay? But of course, this equivalence is lost when this happens, okay? So up to this point, anyway, the point is that in the radiancy limit, up to this point, you cannot distinguish the isospin chemical potential and the baryon chemical potential, okay? So anyway, so that you can confirm, you can see explicitly using this very simple description, okay? So let's go into the final part of my lecture. That is about the magnetic field and the inhomogeneity. So actually, there are several very good reasons to think about the magnetic field. And magnetic field, I mean the U1 magnetic field, not the chrome magnetic field, but QED magnetic field, okay? And usually, the QED effect is a small correction to QCD physics, because the QCD typical scales are scale is lambda QCD, that is 200 MeV, and obviously the U1 field, QED fields are small corrections to QCD physics. But if the magnetic field is strong enough, if this energy scale is comparable to lambda QCD, of course you should not neglect magnetic field at all. Or you can expect some very non-trivial and interesting effects of the magnetic field on quark matter, right? And in fact, that is the case if you look at the situation created at the heavy ion collision experiment, okay? So this is a schematic picture of the heavy ion collision viewed viewed from above, okay? So here you have positively charged heavy ion, and here you have positively charged heavy ion. And so they collide with some impact parameter. So this is a non-central collision, okay? And then this system can be viewed in this way, okay? So this is effectively a system with circular current, right? And then because you have a circular current, it is quite natural to expect some magnetic field created by this current, okay, in the direction perpendicular to this plane, okay? And you can make a rough estimate by using linear Behe potential. So for a point-like particle, of course, this is a very complicated system with spectators and participants, etc. But okay, for the first approximation, you can approximate this extended object as a particle, okay, as a point particle, and then you can solve this problem analytically, and then so this is a profile of the magnetic field as a function of time. And the analytical form is given by this, with a typical strength and a typical time scale. Okay, and this B is the impact factor. So this is the separation between two heavy ions, and this is something that can be fixed by the experimental situation. Okay, so this B is typically something like one of order of 1 femtometer. Okay. Because the radius of the gold atom, the nucleus is 7 femtometer, and so this impact parameter is something a few MeV, a few femtometer or something. Okay, so this is of order 1, and this Z is of order 100, and this hyperbolic sign Y is the beam rapidity, and this is something like 5 or something, depending on the beam energy. But anyway, so here you see this is 10 MeV squared. So this typical energy scale of this produced magnetic field is 100 MeV. Okay, this is quite comparable to the QCD scale, lambda QCD. Okay, so it is very natural to expect a significant effect coming from the magnetic field. Okay. And one very famous example is the chiral magnetic effect. Okay? So if you have very strong magnetic field, and if you have right-handed fermions and left-handed fermions, then you can expect something very interesting. That is, right-handed quarks must have the momentum and spin parallel to each other. This is a definition of right-handedness, right? And for left-handed quarks, the spin and momentum should be anti-parallel to each other. And because the magnetic field is so strong, the spin direction is completely aligned in the direction parallel to the magnetic field. And so, accordingly, the momentum direction is fixed, right? And then you can generate the flow of the right-handed quarks and left-handed quarks. And so, if there is any imbalance between the right-handed quarks and left-handed quarks, namely some finite value of the chiral charge, then you can expect a finite current, okay, finite electric current. So, this is a very classical intuitive picture of the chiral magnetic effect, okay. And this, the chiral charge can be expected from some topological effect or some initial condition, okay? Anyway, so if this is the case, then you can have some current. Okay. So this is the chiral magnetic effect, and so this actually this effect has an anomaly origin, and so that means the final expression is very simple without without any quantum corrections. Okay, this is an exact formula. Okay, between generated current and the magnetic field with the chirality. Okay, and actually there is some analogous relation between the charge density and the actual current. Okay, so here this is a relation between the actual charge and the vector current, but okay, for the vector charge and actual current, you can have the same relation, and this is called the chiral separation effect. Okay, and actually you can combine this relation and this relation to get the wave equation. Okay, and so this is called the chiral magnetic wave, and this was proposed by Lima, Kapseyev, and Yi in 2010. And actually, this has a very interesting experimental consequence. Okay, so let me sketch the idea. Okay, so let's suppose you have a strong magnetic field in non-central collision, and if you have finite density in this region where you have hot and dense medium, okay, then naturally you have actual current here. Okay, according to this chiral separation effect. Okay. And that means that means here you have more right-handed particles, and here you have more left-handed particles. Okay, and now you have a positive chirality charge here and negative chirality charge here. Okay, with magnetic field, and so according to chiral magnetic effect, you can have the electric current. Okay, and then you have positive charge here and negative charge here and here, because the chiral charge is opposite. Then the direction of the current is also opposite. That means here you have more positive current charge and here you have more negative charge. And this means, so you have a quadrupole moment in the distribution of the electric charge. Okay, and then this is a very interesting observation. Why? Because the elliptic flow is a very important observable in the heavy ion collision experiment, and elliptic flow is actually the imbalance between the particles emitted in this direction and this direction. Okay, and usually you have more particles along this direction rather than this direction because you have more stronger pressure gradient. Okay, along this direction rather than this direction. Okay, but because plus charge, you have more plus charge here. That means you have more pi plus here. Okay, and that means so this is some effect against the elliptic flow. You have more pi plus here and here rather than here and here. That means if you measure the elliptic flow for pi plus and pi minus, it is a natural anticipation that you have less elliptic flow for pi plus and the bigger elliptic flow for pi minus. Okay, and this is indeed so. So this is experimental data. Okay, as a function of some charge asymmetry. Okay, so this essentially measures the density. Yes, and actually, so this is a prediction by these people based on the chiral magnetic wave, and so far, so it is not very easy to see the plot. Okay, the dots. But here, the experimental data, if you take the difference between these two values, then actually this has some straight line behavior that is quite consistent with this estimate based on the chiral magnetic wave. So far, this chiral magnetic wave is consistent with the experimental data. Okay. So this is very interesting possibility. And so all these interesting phenomena, yes?
sorry to interrupt. You started with your discussion with chiral charges,
Yes.
but there's no conserved chiral charge, right?
Oh, that's a very good point. Yes. Yeah, in fact, to derive chiral magnetic wave, I assumed one very important thing. That is the conservation of actual charge, actual current.
But you know it's not true.
Right, right. This must be corrected by FF dual. Okay. So if you take account of the topological term, that gives you the diffusion of this the wave mode. Okay. So that is actually neglected in the discussion by them. So yeah, it's indeed the crucial point. Yes. Yeah, very good point. Yes. So anyway, so okay, even though the argument is quite consistent with the experimental data, there are lots of background effects, and so there is no clear-cut argument of why. So this should be the evidence, clear evidence for this the chiral magnetic wave. Okay. So this definitely needs further investigations. Yes. But anyway, so to understand very interesting phenomena induced by the magnetic field, it is very useful to consider the dimensional reduction, and to understand that you have to understand the Landau quantization. Okay, so this is the energy dispersion relation of charged particle in magnetic field. Okay, so this is a very generic expression for spin S particle. Okay. And the transverse motion is quantized in such a way that is equivalent to the harmonic oscillator. So the transverse means the perpendicular plane to the applied magnetic field. Okay. So along the magnetic field, nothing happens. Okay. So this part is not changed, but the transverse plane. Intuitively, the charged particle should move. Should make some circular motion, okay, and then that is on the quantum level represented by the harmonic oscillator in this way, okay. And so here you have the 0-point oscillation energy, okay. And so here, so this is a coupling between the spin and magnetic field. And the important observation is that for spin 1/2 particle, that is fermions like quarks or electrons. Okay, so this spin half means, so here you have negative G's, the charge, okay, electric charge or whatever, anyway, the charge of the magnetic field, the charge that couples to the magnetic field, but anyway, so, okay, minus GB means that this exactly cancels this 0-point oscillation energy, okay, and so for spin 1/2 particle, you have 0 mode. Okay, so this energy and this energy they cancel exactly. Okay, and so this is very important observation. And if the magnetic field is very, very strong, actually this 0 mode is the dominant mode. Okay, because all other modes are largely gapped by this term, okay, B. Okay. So, in the limit of the infinitely strong magnetic field, the charge systems live in 1+1 dimensions only. Okay, you can forget about this transverse motion, but the D direction that is parallel to the magnetic field, okay, this is only relevant direction in space, and also you have time. So this is naturally 1+1 dimensional system, okay? And then in 1+1 dimensions, you have lots of interesting relations, okay? For example, this is a very suggestive relation of the gamma matrices in 1+1 dimensions. So here, actually in 1+1 dimensions, the vector current is related to the actual vector current, okay? Because in 1+1 gamma mu gamma phi is actually given by this epsilon mu nu, so this is an anti-symmetric